Hey guys, happy May Day. I just thought I'd do like a little short screencast that kind of takes us through section two and starts on section three. We've been learning about changes in the sky. Section two, you're basically using trigonometry and you're also using geometry and math to figure out angles, measuring the angular distance. So we can do this by measuring objects in the sky by using the fist method. So we know from going from our horizon to straight up, that's 90 degrees. So we just calculate how many of our fists will fit in there. And you can also figure out how many thumbs, you do something like this, how many thumbs will fit into a fist. So earlier I did an experiment where I measured the angular distance from that method and using trigonometry. So I'll just show you a couple things on the trigonometry method. So 7 fists, each fist is going to be about 12.86 degrees. And then a thumb, since it goes into a fist, you take 12.86 and 4 thumbs. That's how many, I had 4 thumbs that fit into my fist. So it's about 3 degrees per thumb. So I added those up and I'd have to calculate how many fists fit in an object and how many thumbs fit between two objects and then measure that. The second method for measuring the angle of the sun is you take the gnomon length and the shadow length, and you can use trigonometry. So if you look at this little diagram, we have the TOA method. Tangent of theta is equal to opposite over adjacent. So the gnomon length would be the opposite, and the shadow length would be adjacent. So like if it was 1 centimeter and the shadow was 1 centimeter, then this would be at a 45-degree angle. So you can use trigonometry. So that's basically what section 2 is about. It also has discussion on if you have an object. I think this is from 2.4. If you have an object that's sticking up and it has a shadow length, and then if that's on a building, and then you have something on the ground, the sun is so far away that its rays are going to be parallel. So we know that that's kind of evidence that the sun is really far away. Let's see. So it also talks a little bit about local noon. There's something on my slideshow that tells you another way of finding local noon. You can actually take these times, figure out how long the day is, and then you figure out the halfway point, and that's going to be local noon. Okay, so we kind of leave off on when we start section 3. There's a surveyor that says that the mountain is like 2.1 degrees, and then there's a climber that makes some measurements, and you also have to use this trigonometry to figure out how tall that or the angle of that mountain according to the surveyor. So we're going to use tangent. It's opposite over adjacent. So the height of the mountain would be the opposite, and then the length here would be the adjacent. So you can use a calculator. I used Google. You can use different calculators. Your phones sometimes have these. So we have 2.7 divided by 60. When you do an arctangent, you have to make sure that your calculator is in degrees. And then if you do like inverse, you're going to see that tangent minus 1. So then if I just type in 2.7 divided by 60, okay, that's 0.045. So if I take the inverse tangent of 0.045, that gives me this number. So that means that it is, according to the surveyor, the mountain is up at about 2.57 degrees. Now remember the surveyor, so this is the mountain climber. The surveyor said it was 2.1. So that's a pretty big difference. They're pretty big different. They're pretty different. So why do you think if you're standing way over here, you're doing everything right, and you're a mountain climber, and let's assume that your measurements are right, why do you think that they're going to be different? The reason is it's the curvature of the Earth. The Earth is not completely flat, despite what some people might say. And you can actually measure this curvature. You can measure this in the seas. You can see how like you don't see the bottom of ships. And if you're doing like a large scale survey of like 60 miles away, the Earth will go down about 3 feet because of this curvature. And you can use trigonometry to actually figure this out. You can also use these kind of angles to calculate the size of the Earth. So maybe I'll just play this. Oh wait, here I gotta present. This is Carl Sagan. Put this show together in like the 70s. This is the original Cosmos. Thought I'd give you this for some historic context.
Here's a map of ancient Egypt. I've inserted 2 sticks or obelisks, one up here in Alexandria and one down here in Syene. Now, if at a certain moment each stick casts no shadow at all, that's perfectly easy to understand, provided the Earth is flat. If the shadow at Syene is at a certain length, and the shadow at Alexandria is the same length, that also makes sense on a flat Earth. But how could it be, Eratosthenes asked, that at the same instant there was no shadow at Syene and a very substantial shadow at Alexandria? The only answer was that the surface of the Earth is curved. Not only that, but the greater the curvature, the bigger the difference in the lengths of the shadows. The sun is so far away that its rays are parallel when they reach the Earth. Sticks at different angles to the sun's rays will cast shadows at different lengths. For the observed difference in the shadow lengths, the distance between Alexandria and Syene had to be about 7 degrees along the surface of the Earth. By that I mean, if you imagine these sticks extending all the way down to the center of the Earth, they would there intersect at an angle of about 7 degrees. Well, 7 degrees is something like a 50th of the full circumference of the Earth, 360 degrees. Eratosthenes knew the distance between Alexandria and Syene. He knew it was 800 kilometers. Why? Because he hired a man to pace out the entire distance so that he could perform the calculation I'm talking about. Now, 800 kilometers times 50 is 40,000 kilometers. So that must be the circumference of the Earth. That's how far it is to go once around the Earth. That's the right answer. Eratosthenes' only tools were sticks, eyes, feet, and brains, plus a zest for experiment. With those tools, he correctly deduced the circumference of the Earth to high precision, with an error of only a few percent. That's pretty good figuring for 2,200 years ago.
All right. So with sticks, eyes, feet, and brain, you can figure out the size of the Earth. This is basically going just to 3.3. Then you'll be done with section 3. You'll be ready to take the post there. And I just wanted to show you one little diagram. Okay, so this is a very simplified version of what Carl Sagan was just talking about. You have 7 degrees. That is the difference between the shadows. So if we have sun's lights hitting this, and the sun's light's going to be parallel, this is going to be 7 degrees. Therefore, we can say that this is going to be 7 degrees. We know that the whole a circle has 360 degrees. So you can just set this up as a fraction and cross multiply it. So if So basically, if you take 360 times 500, divide that by 7, that's going to tell you what you can put up here, and that's how we can calculate the size of the Earth using our feet and brains and sticks. Have a good day.